All right, let's go ahead and get into the main use of the correlation coefficient. So last time we observed that the correlation coefficient is a way for us to essentially check our claims that were made just from the qualitative, in other words, what we feel is true about the relationship. And the correlation coefficient is a more subjective way for us to describe that relationship. So when we use a scatter plot, that's very subjective. If you claim that there's a pattern, someone might not see a pattern or might not believe that the pattern is very strong at all. But the correlation coefficient is a way for us to be more objective. So that's one of the things that you want to know. The correlation coefficient allows for objectivity. And not only does it allow for objectivity in our claims, but it also allows us to essentially justify that there is a statistically significant relationship. So if we take a look at any scatter plot, so for example, maybe if we look at this one right here, it would be very difficult for us to say that there is a relationship because not everybody might agree that there is a relationship shown in that graphic. However, what we're going to do is we're going to say in a previous example, when we went ahead and said that I believe that total income, so that being my explanatory variable, predicted the loan amount that a person was requesting, then I can go ahead and now say, well, if the explanatory variable that you're claiming actually somehow influences the response variable, then there should be evidence of this. And again, this is me trying to show that the x variable, is in fact influencing the y variable. There should be evidence of that because I should see it in the scatter plot and I should see it in the correlation coefficient. So here's the way that it's going to work. We're essentially going to say, this is a hypothesis. I don't know that this is correct. It's what I believe. I think this is true. And it's really important that you recognize that we totally made this up. When I said X is the total income and we believe that that determines the loan amounts that somebody was asking for, we are not, professional bankers or finance individuals. So a lot of times this hypothesis comes from domain expertise. And that's what kind of helps essentially start this process. We're saying we believe, based on my professional knowledge, that this X variable, the explanatory variable, could influence what I observed in the Y variable. And now I want to back that up. And what we do, again, based on that domain expertise, it gives you a starting point. And that's where you go ahead and first create the scatter plot. And then you go ahead and create the find the correlation coefficient. And what we can do from that is we can say, if the correlation coefficient is very strong, and remember that that means that the correlation coefficient R has to be very close to 1, then that will support the hypothesis that the X variable and the Y variable really are tied in some way. They might be influenced, that they're correlated. And what we end up with is we actually end up with our very first hypothesis test, because we know that if these variables really are not related, then the population, so here's something important, rho, Greek letter R, is actually the population correlation coefficient between X and Y. And remember, we don't have access to the population. But if rho is the population correlation coefficient and I sample, then I'm going to end up with my sample, and that creates this scatter plot, the X and the Y from my specific sample. And remember that there's reason for us to believe that if I take a sample from my population correlation coefficient and I get the so from the population, I'm going to end up with the sample correlation coefficient. Kind of like when we went ahead and we're interested in the mean and we took a sample, we end up with the sample mean. And there's reason for us to believe that if this is done randomly, then the sample mean should be close to the population mean. And that's the same logic that we're going to use here, because we're assuming we have a valid random sample. So my sample correlation coefficient should be roughly very close to the population correlation coefficient. So if the population correlation coefficient rho is actually 0, then when I take a random sample, I should end up with a sample correlation coefficient that is very close to 0 as well. In other words, I would get a correlation coefficient that is somewhere along here, which would support the idea that there is no correlation because our R value in absolute value is very close to 0. On the other hand, if there really is a pattern in my data in the population, then I expect the population correlation coefficient rho to not be 0. So it could be positive. If it's not 0 and positive, then it could land somewhere over here. And if rho is not 0 and rho is negative, then it'll land somewhere over here. Now, I'm not quite sure where the sample correlation coefficient lands, because remember, this is random, so you're not going to get the exact value of the population, but we do expect that we're going to be relatively close. So in other words, the stronger the sample correlation coefficient is, the more evidence there is that there is, in fact, this correlation or association between the X and Y variable, and what I hypothesized is in fact correct, that there's now statistical evidence to support the claim that the variable that I identified, X and Y, are in fact correlated. And what I want to point out is that there is this cutoff point. So the closer we are to 1 or -1, the more evidence there is. But there does come a place somewhere here where it's not obvious whether the correlation is actually significant or not. So what I've been describing is a hypothesis test for the significance of the correlation coefficient. And as I've already said, rho is the population correlation coefficient. It's unknown to us. It's derived from the population. And what we want to recognize is that when I take a sample, the sample correlation, oh, this is wrong. It's not population, it's sample. That R is the sample correlation coefficient is known to us, and they should be roughly about the same. So rho should be approximately fairly close to R if sampling is done correctly. So if we take a proper sample. All right. And so what we're going to say is we're going to always go according to the null hypothesis. Remember that this is based on domain expertise. So you're just hoping that the variable X and Y are actually related. So because we have no reason to believe that we're actually correct, we're going to go ahead and say always start with the null hypothesis. And the null hypothesis is basically the hypothesis that there's really nothing significant about the variables. It's basically just saying, just to be safe, I'm going to assume that the variables X and Y are not significant. So in other words, the population correlation coefficient is not significant. There is no significant correlation between the two variables that I've identified, because you're basically just shooting in the dark here. You're saying, here's a variable X, here's a variable Y. Let me just see if they're correlated. And we have no reason to believe that any one variable should be correlated with another variable unless we have more knowledge. And again, this is where that domain expertise comes from. So it's pretty safe to say that most variables in the world X would be unrelated to any other random variable Y. So this null hypothesis is basically our safety net. It's basically the safest, how do you spell safest? Safest guess. if so if I were to give you data that you know nothing about, let's say about, some kind of like nuclear reaction, and you have a lot of variables, chances are that most of those variables are not going to be correlated. So that's why the null hypothesis is basically our safest guess. Now, because I'm essentially saying I am an expert in what I'm saying, so therefore I have reason to believe that X is correlated with Y, then I'm trying to say I do not believe that we are looking at this scenario. So in other words, I'm hoping that I can convince you that the population correlation coefficient is actually different from zero. So we're hoping to, again, be different from zero. And that's why the alternative hypothesis, because again, we're experts, so our domain expertise leads us to believe that my chosen quantitative variables, X and Y, actually do interact in some way. And so in the population, if you were to compute the correlation coefficient for those, they would be significantly different from zero. So in other words, there is a significant correlation between the variable X and Y, only using my sample. And so remember, we don't have access to rho, so we're going to say, is the R value close enough to 1? So it's this little number line that we created, and we know that if the population correlation coefficient is not zero, then it's got to be further out to the left or to the right. Then your sample correlation coefficient should also be relatively nearby. And again, this is a probabilistic argument. So here's the way that we're going to do it. We haven't done hypothesis tests yet. It's going to be something that we revisit yet later on. And so the way that I'm going to ask you guys to do it is to use this table. Based on the number of points that you have, the number of points actually allow you to determine whether there is a relationship or not. If you have 100 data points and there's this little cloud, actually, you know what? We already did this. If you have a lot of data points and you get a pattern like this, then it's, again, not very strong, but because we have so many data points, there seems to be this trend upwards, generally something like that, except for these points. The fact that I have so many points following that trend strengthen the claim that there is a relationship, even if, 1 or 2 points don't follow that trend. Generally, the more points you have, the more spread out your data can be, and it'll be more obvious to most individuals that there is, in fact, a relationship. So the cutoff point, so here we go. When you take a sample, if you land close to zero, that's no good. And that should be obvious. If your sample correlation coefficient is close to zero, that's no good. So if you get any R value in here, that's, again, not very convincing that the population correlation coefficient is not close to zero. Now, if you land very close to 1 or -1, then that's obvious evidence that there does appear to be some kind of correlation or association between your X and Y variable. And so there is going to be this cutoff point, kind of like the upper fence and lower fence. And that's called the critical value. The critical value is going to be the cutoff point at which we're going to say we do, in fact, have a significant relationship. And that's called R star. So R star is going to be your value to beat. So the critical value, again, and I said it, it depends on the number of data points that you have. So the R value is called the critical value, that's R star. And so depending on the number of data points that you have, so if you only have 3 data points, you need to have a sample correlation coefficient stronger than 0.997, either positive or negative. So what we're really doing is we're going to say the critical value R star is basically the value that our sample correlation coefficient, and again, that's just R, needs to beat, essentially, or stronger than. And remember that to beat means that you're closer to 1 than this particular value. And it should make sense why, if you have 3 data points, you need a very strong value. Because look, to make a line, you just need 2 data points. So that for sure will follow a line. So there's no critical value to beat. But if you add a third point, and let's say your third point is out here, it's hard to argue that that right there is a strong relationship, unless the third point is very close in between these two like that. So then your oval would be very, very small. So that, I think most people that see something like this would say, oh yeah, it looks like there's a trend. So in other words, you don't have a lot of leeway if you have a small number of data points, because then if your data is over here, you would have a hard time getting most people to agree that that is in fact a trend. However, if you have, for example, 20 data points or 50 data points, kind of like how we had with the loan data, then you can see that the R value to beat decreases, because it's easier to say that there's a trend if you have a cloud of points and they're all more or less following a trend. So even if you have a lot of points like that, you can be very close to 0, and that'll still provide evidence that there does appear to be some trend or some pattern in our data. So here's the last point that I'm going to make. To show that there's a statistically significant pattern, so in other words, there's a statistically significant trend or association between our selected variables, X and Y, because I believe that there's a reason, we're going to go ahead and just check. So we're going to check whether our correlation coefficient, so that is closer to 1 than the critical value. And this should make sense because you're ignoring the sign. So R star, let's say, is here. You want to be higher than that over here. Now, if you have a negative trend, then you're going to look at R star over here on the negative side, but you want to be closer to -1. So again, the way that you do that is you just drop the absolute, drop the sign. All right, let's go ahead and take a look at one example, and then you'll do the rest of it. So here is our first example, 4.125. Gallup organization regularly surveys adult Americans regarding their commute time to work. In addition, they administer a well-being survey. According to the Gallup organization, the Gallup Healthways Well-Being Index composite score is comprised of 6 sub-indices. So in other words, we're looking at 2 variables here. We're looking at the commute time, that's one variable, and we're also looking at what's called a well-being index. So an index is basically a way to track something or to compute a new number based from additional data. And the way that they track well-being is pretty interesting. They are looking at, in other words, your life evaluation, your emotional health, your physical health, your healthy behaviors, work environment, and basic access. So I'm not quite sure what that is. But in other words, there's a long kind of survey or some kind of assessment that they do. And all of these scores that you obtain are then computed into one score that is called the well-being index. And we have the following data. So remember that this is a data frame. What you see here on the right-hand side is the data frame. And the data frame is just a way for us to organize our variables, individuals' data. So in other words, here's person number 1, individual number 1. And they have a commute time of 5 minutes, and they have a composite score of 69.2. So every row is an individual, every value here is data, and we can see here we have the variables. All right. So let's quickly go ahead and answer part A. Which variable do you believe is likely the explanatory, and which is the response? So that simply is saying which variable do you believe is influencing the other variable. After some thought, I hope that you reach the conclusion that the explanatory variable X should be commute time. Because I have reason to believe that if you're spending a lot of time driving around, that really does influence your well-being, your physical health. For example, you might not have time to go work out, or might influence the time you have to, cook food, or it might really stress you out if you're in traffic all day. So I really believe that commute time influences the response Y, which is going to be the well-being. All right, as soon as I believe that the explanatory is commute time and the response is well-being, then I should be able to back this up with a scatter plot. So we can go to our notes, our Unit 2 regression notes. It's in our share folder. And we've got our data right here. So let's create our scatter plot. And I'm going to select X is commute time and Y is well-being. And we can see that based on the scatter plot, based on where our data lands, there does seem to be a trend here, pretty strong, I would say. This point is kind of off, but if you were to make an oval, there does appear to be a fairly thin oval. And so I'm going to go ahead and say I drew the scatter plot. Does there appear to be a relation? The answer is yes. There is a linear association, and that association is negative and fairly strong. So let me just go ahead and say strong negative. From this observation, I can go ahead and now determine the linear correlation coefficient. Remember, always do this first. Now we can determine the linear correlation coefficient. And to do that, that's a statistic. So I'm going to go to stats, summary stats, and go to where it says correlation. Then you simply select both variables of interest. Remember that you can press Control or you can click and drag. And that's fairly it. That's all that you have to do. And we have our correlation coefficient of negative 0.9805. So the sample correlation coefficient here is negative 0.9805. And what I want to point out is that this does in fact support the following assumptions. Notice it's negative. That means that there's a negative trend. And then 0.98 is close to 1, which means that I have a strong correlation. All right, now part D asks, does a relationship exist between commute time and well-being score? So does a relationship exist between commute time and well-being score? Here is where you got to ask yourself now, is this value close enough to 1? In other words, does this sample evidence, so we're basically saying, does the sample, because this is just a sample, we didn't ask, the entire world, does the sample provide evidence of a trend? In other words, that the population correlation coefficient is not 0. In other words, that there is some, positive or negative value. And this is where we have to do our test. So the first thing you got to do is you got to find the correlation coefficient. You got to say, what is the correlation coefficient that I need to beat? So we're basically saying on this number line, so remember R is a way to standardize. If it were 0, then the answer would be, well, rho is probably 0. But since we're so close to -1, we got reason to believe that rho itself might also be might not be 0. So it could be very close to -1 as well. Now, the way that you do this is you actually got to look at the number of data points that you have. And it's fairly simple because you can see that the data ends at 7. So there are 7 individuals that were surveyed. And you can count 1, 2, 3, 4, 5, 6, and 7. So there's 7 individuals here and therefore 7 pairings. So we're going to go and say, first of all, we have a sample size of 7 here. And there I can go ahead and find the critical value, by going to this table here. Now, this table is actually provided on your reference sheet. So this is something that you can always use on exams. And it's right here where it says critical value for correlation coefficient. So at 7, we see it's 0.754. So at 7, it's 0.754. All right, so we're almost done. Now that we've got that information, we just do a simple comparison. And ours is fairly obvious because the trend is so strong, but we're simply going to go ahead and write the absolute value of my correlation coefficient is the absolute value of negative 0.9805, and that gives me 0.9805. So is our correlation coefficient stronger than this cutoff point? So we want to compare. And the answer is yes, we are closer to 1 than our star. So we are essentially landing in this region right here where it's clear that there is a correlation coefficient, population correlation coefficient away from 0. So we're going to go ahead and write that since absolute value of R is greater than R star, we have a statistically significant correlation. All right, there's our first example, and I want you to go ahead and attempt the same thing, but now for this example that tracks the month, the money spent on advertising, and the number of items sold. So go ahead and do part A, part B, part C, and part D.